Good morning, everybody. Today is May 1st, and it's a Friday, 2020, right? Happy May Day, and Friday. I'm happy it's the weekend, and it's going to be a beautiful day today, so hopefully you get a chance to get out there and enjoy it. Today, you all have an exam, and so this session is really meant to serve as a review for you. I want to review a couple of contents. I'm going to review a couple of concepts that you'll see today on your exam. Your exam will probably be posted at about noon today. It's mostly written. I just have a few finishing touches I want to put on it. It'll probably be around 40 points-ish, something like that. So I don't anticipate that it'll take you more than 30 to 45 minutes to do. It's a relatively short exam, and it covers intermolecular forces, solids, liquids, gases. Most of the gas stuff was in the last unit, but you might see something about kinetic energy and temperature, things like that. And then you're also going to see solutions, which we covered earlier this week. So it's not a whole lot of information on there. So anyway, let's go ahead and get started. I posted a few things on the agenda today that I wanted to remind myself to go over with you. Before I forget though, don't forget that the Instagram extra is available to all. Let me go ahead and make this a little easier to see. There's still people coming in. Hello. Okay, let's go ahead and take a look at the agenda together. That's not what it's supposed to look like, but okay. All right, so I want to remind you that you have an Instagram extra credit opportunity. I'm hoping that you all have got quite a few friends on Instagram, on our Instagram account. You should follow at least 20 or 30 other people. And if they request to follow you, please follow them back, accept their follow request and follow them back. It'll create a nice little network. I love seeing your images of all the chemistry in your lives, lots of candles and cooking. And you're making my mouth water with all those cookies. You guys make me want to go bake some cookies and cakes. But glad to see that you are realizing the positive impact that chemistry is still having on our lives, even though we're all in quarantine. So don't forget to go do that. I'll probably sit down tonight or sometime this weekend and go through the Instagram and give you guys that extra credit. So please make sure you post it by today if you haven't already. And then we'll see if there's another one that I can post up for next week for you all. What else? Oh, kudos to Kale also. Kale, are you in here? I don't know if you're here today or not. You probably are. Kudos to you. I saw your campaigning for student body something, president maybe. He posted something up on the Instagram page. What a smart way to get your name out to lots of different sophomores. So I enjoyed seeing Kale get attacked with color. If you haven't seen it, go follow him and take a look. It's worthwhile. Let's see. Today, I wanted to go over this preparing solutions and dilutions. We're going to review a couple of those calculations. Oh, there's Kale. He was in the. Hi, Kale. I just gave you some props, and you weren't in there, but I just told everybody about how much I enjoyed seeing your campaigning for students.
Oh, thank you. Thank you.
It was very enjoyable to watch you get attacked with color. So I told everybody to go check you out and follow you on Instagram. What a brilliant way to meet to get your name out to so many 10th graders.
Thank you.
Good luck. When are votes?
Monday from 10 to 4.
Oh, okay. Okay, everyone go vote for student body. And you're running for president, Kale?
Yeah.
All
Yeah.
right. Good luck to you.
Thank you.
Okay, so we're going to review our lab calculations today. There were a couple of questions about that, so I just want to make sure that that's clear. We're going to talk about something called pitch, and then I've got a couple of a cartoon and some solubility curves for you, and then I'll answer any other questions you all might have at the end of the period. So let's go ahead and get started with the lab calculations. I actually did not get a chance to upload my answer key for you all, but I'll just hold it up in front of the screen. I think most of you turned this in today. Okay, you're preparing solutions and dilutions lab. And again, this is one of the most important concepts I could teach you, is how to make solutions. And some students were questioning how to do the calculations here. So firstly, I just wanted to go over the answers. I'll just hold it up like this so you can see it. So for question number 1, you were making a stock solution that's a 0.5 molar sodium chloride. So it's just table salt, right? So you should have gotten 2.9 grams of sodium chloride there. And then the percent by mass of sodium chloride in the stock solution, you just take the mass of sodium chloride divided by the mass of the entire solution, and you can assume that the solution mass is 100 grams because it's 100 milliliters. It's slightly off, but anyway, it's just a part to whole ratio, and it's about 2.9% sodium chloride. And then some students were asking me too, what do I do for number 2? Because I didn't actually make the solution. Just pretend that you made the solution. So hopefully you guys just filled something in there. And then the next part of this was to dilute that stock solution down to a new concentration using the equation M1V1 equals M2V2. And so you should have found that you needed 6 milliliters of your stock solution. And then to get the percent by mass, again, that percent by mass calculation is in the text box on the very front cover. So it's a percent by mass. It's just like when you calculate your percentage on an exam, you get the total amount that you got right divided by the total possible, right? The percent by mass of solute is just going to be the mass of solute divided by the total mass of solution. So it's just a part to whole ratio, okay? And times 100 will give you a percent. So you should have gotten something there, assuming the mass of the solution was 100 grams. You should have gotten something around a 0.18% by mass there because you diluted it down. And then describing steps you took would just be, take 6 mils of your stock solution and then fill your volumetric flask up the rest of the way with water to the line. And that's it. Don't forget that one of the things that I would look out for had we been doing this lab is you always want to measure to the bottom of the meniscus, right? So you would see a meniscus formed here because of water. Remember, water's ability to form strong intermolecular forces allows it to grab onto the glass, and it forms this sort of U shape that's called a meniscus. And you'll see that in volumetric flasks too. So you always want to make sure that the bottom of the meniscus is at the line. And so when I have students actually perform this lab, I'll make you come up to the front of the classroom and show me your solution, and I check you off. I would normally put a stamp in here if you made it correctly. But I would ask you a series of questions, and one of the things I would look for is that the bottom of the meniscus is right at that line on the volumetric flask, because that's where it's going to be a really accurate volume, okay? And remember, volumetric flasks only have one line on them, and that line is super duper accurate to whatever volume the flask is, okay? So we have 100 milliliter volumetric flasks, we have 500 mils, we have 1 liter volumetric flask. I even have 2 liter volumetric flasks. They're ginormous. But anyway, you just choose whichever size flask you need based on how much solution you need to produce, okay? So very important skill for a chemist to have. Are there any other questions about this lab or how you were supposed to approach it or the calculations that you'd like me to go over? Okay, and I will go on. The next thing I wanted to review with you was, let's go back and look at that agenda. What did I put here? Oh, pitch. You guys, refresh my memory. I feel like I did pitch as a molecule of the week once before. Have you ever heard of the pitch drop experiment? Have I talked to you guys about this?
Yeah, I think so.
Okay, good. I just want to refresh your memory about that then. So let me go ahead and pull this up. I'm glad I've already talked about it. So we'll just refresh your memory. Just a minute here. I thought I had done it as a molecule of the week. Man, I'm telling you, I'm in my 40s now. Getting old is no fun. It's crazy how you just forget things. Here we go. This was a molecule of the week a long time ago. Can you see my screen now with pitch on it? I hope you guys can see that. If you can't see it, someone speak up. But I want to remind you what pitch is. I passed it around to you in a little baggie. It looks like a solid, but it's actually a very viscous liquid. And I want to bring up this concept of viscosity again, because viscosity has everything to do with intermolecular forces. And we haven't talked about intermolecular forces, or we hadn't talked about intermolecular forces when I brought this up to you. I think that when I made this molecule of the week, I was talking about intermolecular forces with my varsity chemistry students. And so I wanted to bring it back up again just to refresh your memory. So pitch is a substance that looks like a solid, but it's actually a very viscous liquid. And I want to remind you about this pitch drop experiment that is the longest running scientific experiment in the Guinness Book of World Records. It's taking place down in the University of Queensland in Australia. And anyway, you can watch a live stream of the pitch drop, and we see the dates recorded as to when the drops fell. And at this point, we're waiting for the 10th drop to fall. And it seems like it's taken about every 13 years, this pitch drops. Now, pitch is really just a hydrocarbon. It's just a really long chain of hydrocarbons. And so it's kind of surprising that it's such a viscous substance. So I want to just take a mental snapshot of this, because I'm going to take this off screen share in just a moment. But look at this substance, how thick it is, and obviously it drips very slowly or oozes very slowly. And the reason why has to do with the fact that it has really strong intermolecular forces. Now, this is counterintuitive though, because pitch is it's a hydrocarbon. Okay, so pitch, let's see this pen here. Pitch is just a hydrocarbon. I'll call it CXHY. Okay, now we know that carbons and hydrogens have very similar electronegativities. Okay. So really what pitch is just this long chain of carbons with enough hydrogens around it to give all the carbons 4 bonds, okay? I'm not gonna draw in all the hydrogens. But you can imagine that if we have 2 molecules of pitch right next to each other, okay, and enough hydrogens there to give all the carbons 4 bonds, okay, just imagine that I've drawn hydrogens all around. Well, because carbon and hydrogen have almost identical electronegativities, so I'm trying to reduce this glare here for you guys to see better. I don't know if that helps or not. Let's see. Maybe that's a little easier to see. Anyway, it's carbon and hydrogen have almost identical electronegativities, and that means that it's a really non-polar molecule, right? So hydrocarbons are always really non-polar. And so if I were to ask you to think about this for a moment, God, this glare from, sorry, hold on just a moment. I don't know if that's any better. Gosh, this little guy right behind me is glaring on my screen. I don't know if it's glaring on yours, but hopefully you guys can see what's written on my whiteboard there. Anyway, it's not very nonpolar, which means electrons are shared very evenly between carbons and hydrogens. Hydrocarbons are always really nonpolar molecules. So that means the only type of intermolecular force that could exist between these, if you had to choose, remember you have a choice between London dispersion forces, which is like they're linking pinkies with each other. Dipoles would be like holding hands, and hydrogen bonds would be like these really strong hydrogen bonds. Well, because they're nonpolar, the only type of intermolecular force that could exist is London dispersion forces, LDFs, right? Which means they're really weak forces of attraction holding them together. Sort of counterintuitive to think that the weakest intermolecular force produced such a viscous substance. And the reason why has to do with the fact that there's all this surface area, okay? When you have a lot of surface area, even LDFs can actually be really, really strong. Not individually, London dispersion forces are going to be really weak individually, but collectively, all of them together across all the surface area could produce such strong interactions that it makes something a very, very viscous liquid. So it makes it really thick and oozy. So this really, we're going to get into a lot more in varsity chemistry next year, but there are times at which LDFs are stronger than, say, hydrogen bonds, right? Now, hydrogen bonds, if you're just comparing them side by side, remember, hydrogen bonds are definitely the strongest, followed by dipoles, and then LDFs are the weakest, right? So we have weak to strong, okay? And then, so just side by side, if I were to compare a hydrogen bond to an LDF, the hydrogen bond is going to be stronger every day of the week and on Sundays. But sometimes you can have a whole collection of LDFs because of a lot of surface area, and it's the combined LDFs along a very long surface area can actually make something like pitch a really, really viscous liquid. So usually I would say, my point being is that usually the higher, the greater the intermolecular force, or the stronger the intermolecular force, the greater the viscosity of a liquid. And viscosity is simply a resistance to flow. Okay, so obviously that pitch is a really, really viscous liquid. It's very resistant to flow. Okay, but even though it has only LDFs, it's that surface area, a lot of surface area and a lot of very weak intermolecular forces combined that are making it a really viscous substance. Okay, so I just wanted to touch on that and just bring up viscosity one more time now that we have a better understanding of London dispersion forces. Okay, next, what else is on my agenda for today? And you guys pipe up if you have a question, please do let me know. Let's take a look at a cartoon next. I have a cartoon and solubility curves I wanted to show you. So let's see. No, that's not what I want to do. There we go. Okay. Now you guys should finally understand this cartoon. Whoops, where'd it go? That's not what I wanted to do. There we go. All right, I'll give you a moment to read that. All right, so we have sodium chloride here. This would happen if you actually look through our Instagram. You'll see some people showing pictures of themselves putting salt in spaghetti water, and that's their chemistry for the week. So this is a silly little cartoon about salt being put into water and dissolving. So here you've got sodium and chlorine together saying, I just love hanging out with you, right? Opposites attract. They're a nice, happy ionic compound. Oh no, water comes along and then they get separated. They get pulled apart from one another. And so I want you to think for a moment, what type of intermolecular force is being represented in the bottom here versus what type of intermolecular, I shouldn't even call it intermolecular, but what type of interaction is happening up in the top. So the interaction between the sodium and the chlorine in the first picture is different than the interaction being shown in the third picture. So think for a moment, what might it be? How would you describe the bonding here versus the bonding here? Well, in the top picture, you have an attraction between a cation and an anion, or a metal and a non-metal, and that's an ionic interaction, right? So up at the top is ionics. Let's go ahead and label that. That's a bad color to see. A little bit better. Down at the bottom, however, we have an attraction between an ion and a polar water molecule. Remember, water is a polar substance. You watched a couple videos on that. So this is what we call an ion dipole. Ion dipole interactions are actually pretty darn strong. They're even stronger than a hydrogen bond. So I'm going to take this off screen share in just a minute to show you. So remember, these are all what we call intermolecular forces, IMFs, intermolecular, meaning between molecules, okay? But I could also add ion dipoles to this. Color. Ion dipoles are even stronger than hydrogen bonds. Okay, I don't like calling them an intermolecular force because technically it's not between two molecules, it's between an ion and a molecule. So it's, you know, just a wording thing, but me personally, I don't like referring to it as intermolecular because it's not necessarily between two molecules, it's between an ion and a molecule, as shown in the cartoon. And then up at the top, we would have those ionic bonds, covalent bonds, and metallic bonds that are stronger than any of these others, right? Remember, ionic bond is between a metal and a nonmetal, or a cation and an anion. A covalent bond is between two nonmetals, and a metallic bond would exist between two metals, okay? Ionic bonds are stronger than any other type of intermolecular force, okay? But remember that this is the reason why we put salt in spaghetti water. As a matter of fact, I know I have a student who had this discussion with his mother the other day. He was telling me that he was putting salt in the spaghetti water, and his mom said, lots of moms think, that it actually makes your water boil faster, and it's the opposite. In reality, when, you know, normally, water boils between 0 and 100 degrees. I'm sorry, water exists as a liquid between 0 and 100 degrees Celsius, right? But when you add salt to that spaghetti water, you actually increase the boiling point up to something above 100 degrees Celsius. So it actually takes longer to boil. And the reason why, if you think about what's happening there, grab my models, right? When you add that salt to the spaghetti water, what's happening is you're creating those ion dipoles, and these become even stronger than this interaction is stronger than, there we go. You know, when the water molecules were by themselves. So if you just had water, we would have these just hydrogen bonds occurring between two water molecules. As a matter of fact, look at this. This is fun. I can pull them all up, right? And you can see all those hydrogen bonding going on. That's like capillary action, right? The movement of water against the flow of gravity, all because of hydrogen bonding. You get all kinds of cool properties of water because of its ability to make hydrogen bonds. But once I start, so normally if you try to boil water, you've got to break those hydrogen bonds so that they can become gas molecules, right? And be individual entities that are flying around like crazy, like gas molecules do. But if I add salt to that spaghetti water, now I'm not breaking hydrogen bonds, I'm breaking an ion dipole interaction. And ion dipoles are stronger than hydrogen bonds. So it actually takes more energy to break apart that water and get it to boil, because that interaction that has to be broken is a stronger one. That makes water boil at a higher temperature. You've got to add more energy. You got to give these molecules more kinetic energy before that bond can be broken so that they can become a gas. Okay, so that's kind of an interesting point that I wanted to bring up, and thought it was a kind of a cute cartoon I wanted to show you too. All right, on to the next one. Next thing I wanted to review with you is something you haven't seen before in graphical form, but you have seen it. Let me find this here. You have seen it in a demonstration. So I want to remind you about that demonstration that I did back in the classroom with supersaturated sodium acetate. What am I doing here? This is not what I want to show. Nope. Oh, how do I get out of this? I'm sorry, you guys. Hold on just a moment. That's it. Okay. Where is it? There it is. Okay. So I want to remind you, we've already learned solubility rules, right? Remember NAG-SAG and PMS and Castro-Bear that are the exceptions. And we talked about what makes a solution saturated, means you've added as much solute as you possibly can to it. But what I haven't shown you yet is something called a solubility curve. And this solubility curve kind of helps you understand the relationship between temperature and the, let's see what, the amount of solute that will dissolve. This is something I've told you about before. I've called it the Swiss miss effect, where the idea is that if you increase the temperature, you can actually get more of a solute to dissolve, right? If you get something hotter, you can dissolve more substance inside of it. And so that's why, you know, when you put sugar into cold water versus sugar into hot water, you're gonna be able to get more sugar to dissolve in hot water. Okay, because it's solubility is temperature dependent. Most substances, if you increase the temperature, you'll increase the solubility. And that's shown here in this curve. If you follow this curve, you'll see that there's a directly proportional relationship, right, between, you know, temperature and the amount of solute that will dissolve in 100 grams of water. Now, that's what we call a saturated solution. Saturated means you get as maximum amount that you can of solute to dissolve. Anything less than that is going to be unsaturated, right? And anything more than that is what we call supersaturated, okay? And so if you remember back, there was one of the videos I asked you to watch where I made a supersaturated solution of sodium acetate. Do you guys remember this? Do I need to show it to you again, or can you give me a thumbs up if you remember? I hope you do. I went back to the lab and I filmed a video of supersaturated sodium acetate. Ooh, I'm not seeing any thumbs up, which makes me think maybe you guys don't remember it. So I'm going to show you the video clip one more time, because it's probably a good thing for us to review this morning before your test. So let me find it. Where did I put that? Oh, it's on my YouTube channel. If it's not here. Nope, I'm not seeing it there. Darn it. Okay, let me find it another way. Let's go. I'm pretty sure I put it there. There it is, supersaturated sodium acetate. Let's watch.
Hi students, it's me, Mrs. Nielsen, and I'm back at Miracosta High School in my lab and wanted to do a demonstration for you involving some solution chemistry. Now what I have here is a supersaturated solution of sodium acetate. And sodium acetate is an ionic solid at room temperature. As a matter of fact, it's what we call a trihydrate. So you can see here, this would be what it would look like in terms of particle view, where we have the sodium ion, the acetate ion, and then 3 water molecules associated with it. Now, what I've done here is I've made a solution, okay? And a solution contains both solute and solvent. Solute is what's present in the smaller amount, and solvent is what's present in the larger amount. So the way I remember it is that solute is a smaller word, and it's the substance in a mixture that's present in the smaller amount. Now, normally water is a solvent. Water is an excellent solvent. And so what I have in this situation is actually switched. Water is the solute. There's just a little bit of water, and the vast majority of this is sodium acetate. So sodium acetate is supposed to be a solid at room temperature, but you can actually trick it into being a liquid at room temperature. And that's what I've done here, where I have a bunch of sodium acetate, just a little bit of water, and I've melted it down on a hot plate and let it cool back to room temperature. And essentially what I've done is trick it into being a liquid or an aqueous solution at room temperature, when in fact sodium acetate is supposed to be a solid. Okay? And the way I can prove this to you is I can actually shock it back into its solid phase by simply adding a single crystal of sodium acetate. And what I'm doing is agitating the solution just enough to make it turn back into a solid. So if you can see here, I just have a single crystal on my scoopula, tiny, tiny amount. I'm gonna go ahead and just add this into my container. Hold this closer so you can see what's happening. You can see that all of those molecules are starting to just grab onto one another, and they're crystallizing, they're forming back into a solid right before your eyes, back the way they're supposed to be in the solid phase at room temperature. And you can see there's no trickery here. Okay, this is a solid now. Now, if you can feel it, it's also very exothermic, because those molecules are going from having kinetic energy as a liquid back to less kinetic energy as a solid. And what happens to all that extra energy? It gets released as heat. As a matter of fact, this is the same substance they use in commercial hand warmers. Okay, so I hope you enjoyed that demonstration of a supersaturated sodium acetate solution.
Okay, good. So some other things I would point out to you there, if we were actually doing this in class. This is a fun demo to do. I have to say, it's one of my favorites. They all are part of one of my favorites. Anyway, the fun thing is that I was walking around the Hermosa Beach Fair, and they were selling these hand warmers. And if you've ever looked at those commercial hand warmers that are reusable, they often have this little disc, like a little metal disc in there. And what you have to do is you snap this disc, and the snapping is the agitation that shocks that solution to being back into a solid. And so I was over in Hermosa Beach, shopping around their hometown fair, or their fairs. It's not called the hometown fair in Hermosa Beach, but you guys know what I'm talking about. Anyway, and the lady was selling these to me, and I said, "Oh, what's inside there?" And she goes, "I don't know." And I said, "I'll bet you it's a supersaturated solution of sodium acetate." She got this big eyes, this look on her face that kind of freaked her out. I love dropping knowledge on people when they least expect it like that. So you guys, don't be afraid to drop your knowledge on your parents and people around you when they least expect it. So supersaturated solution of sodium acetate. And what happens is, just like that little crystal that I was able to drop in there and agitate the solution, the little metal disc does the same thing. So it just, that little bit of disturbance is enough to make it turn back into a solid. Sometimes when I do this demonstration, just the simple act of taking off the rubber stopper on the flask is enough to make it turn back into a solid, and then I got to melt it all down again. Sometimes just setting it down on the lab bench will make it shock back into a solid. So it's really very, very sensitive. There's some really cool magic show tricks. I don't know if you guys know a senior, his name is Dexter Brown. He did this same exact trick in a really cool way, that's up on my YouTube channel under the magic show, where he poured the solution out onto, he did this for our magic show last year. He poured it out onto a piece of saran wrap. And on that saran wrap, he had just a tiny crystal of sodium acetate. And so when he poured the solution out, it all of a sudden solidified into a mountain of solid. And so that's a pretty cool one too. I'm sure you could find it on YouTube too, if you wanted to look at it that way. It's just kind of a pain to get it all back into the container. So I don't normally do it that way. Anyway, there's lots of different ways of doing this trick, but that little crystal is called a point of nucleation, or that metal disc. When you click it, it's called that point of nucleation. Or if you've ever been to, if you've ever done one of those, use one of those hand warmers while you're skiing, usually you'd have to break it up a little bit. That breaking up action to agitate it, the point of nucleation is the place where everything grabs on, all the molecules grab onto each other and turn back into the solid phase. And it's the same exact thing that happens in cloud formation, actually. We wouldn't have clouds in the atmosphere if there weren't tiny particles of dust in the atmosphere. Those little particles of dust act as a point of nucleation where clouds and water molecules condense onto that surface. So there's another example of a point of nucleation in nature. As a matter of fact, I keep wanting to go outside and go cloud watching with my kids during, for giving us something to do during all this quarantine. And there's not any clouds in the sky ever. It seems like, gosh, let's look outside today. Nope, no clouds in the sky. I'm telling you, we haven't had a lot of clouds lately. And I think it's because there's not as much smog in the atmosphere. We're not driving our cars around. So there's not as many particles in the atmosphere to act as that point of nucleation for the molecules to condense upon. Also, I'll bring it up one other way you may have seen before. If you've ever looked closely at a glass of champagne that an adult is drinking, you'll sometimes notice that there's like this little place in the glass where all the bubbles are starting from. Okay, same sort of idea. That little point in the glass is usually a scratch or some imperfection in the glass that allows the bubbles to grab onto that one point that's a little bit weaker, and that's where the bubbles originate from. So there's another example of a point of nucleation. So this demonstration with the supersaturated sodium acetate only works in really clean glassware. I had to use a brand new Florence flask to do this, because if there's any scratches or any dirt in there, it just won't work. Okay, so sodium acetate is very special in that it'll allow you to make a supersaturated solution so easily. So I want to go back to that graph we were looking at. Okay, and so what you just saw there was a supersaturated solution of sodium acetate, right? So for sodium acetate, we were in the supersaturated range, where even though maybe I was at room temperature, right, or even colder in my classroom, as you all know, I was able to get a lot more solute to dissolve in very little water. So it was a supersaturated solution. Okay, so really all you just, the way you would do this to determine whether the way you would use the graph to determine whether the solution would be unsaturated, saturated, or supersaturated is really just looking at some sort of a temperature and solute amount combination. So in other words, if I had this temperature and this amount of solute, then when they meet together over in this range here, it would be an unsaturated solution. But if I increase the amount of solute to, say, this amount, at the same temperature, then I would be creating a supersaturated solution. And the way you can make a supersaturated solution is by increasing the temperature. You can get more of that substance to dissolve. Okay, so just we'll point out what words are over here too. Every solution has a unique solubility curve, and I'll show you that in just a moment. The relationship between solute, the amount of solute and temperature, they're directly proportional, right? As the temperature goes up, you can get more solute to dissolve. Again, that's what I call the Swiss Miss effect. That idea of pouring the powdered hot chocolate into a cold mug of water versus the powdered hot chocolate into a hot mug of water. And hey, if you're looking for science at home, try it. Okay, if you don't believe me, pour some powdered Swiss Miss into cold mug and a hot water mug, and you'll notice that it'll start dissolving right away in the hot water mug. You can get it to start dissolving. So temperature and solubility are very directly proportional. Solute amount and temperature are directly related. Increase in solute means, what else does this say here? Sorry guys, let's see. Still learning how to use all this stuff. Increase in solute means the need for an increase in temperature to reach saturation. So I want to show you some different substances now. Let me take you back. Where is it? Okay, these are solubility curves for lots of different substances, all on the same graph. And you can see, you know, here is sodium acetate. I don't even see sodium acetate on this one. But most substances have a directly proportional relationship between temperature and solubility. Most of them are increasing curves. There's a couple of them that decrease, right? Like hydrochloric acid and ammonia, so sulfur dioxide. Those are weird, they're unusual. But what my point in this is just to show you that every substance has unique solubility curves. In other words, the amount that you can get to dissolve in water at a certain temperature varies depending on the substance, okay? And we'll get more into that when we get into varsity chemistry too. But that's just something I wanted to point out. You will see a solubility curve on your test today. And I'm just gonna give you something as simple as give you a temperature and solute combination and ask you, hey, based on this graph, is it saturated, unsaturated, or supersaturated? Okay, so I just wanted to point that out to you today. Other than that, I think that's about all that I wanted to go over today. I know that I had some other things that I've given you to work on throughout the week. So I want to answer any questions that you have. Maybe you have questions about this molarity and molarity by dilution worksheet. The answer key was up on Google Classroom, but they weren't worked out. So if you want me to work out any of those, I'd be happy to do that now. If you want me to work out anything that was on the exam review, I'm happy to do that now. Does anyone have questions for me? No? Okay, well, I'm gonna put the finishing touches on your test and it'll be up by noon, no later than noon today. And so I'm just gonna ask that you guys complete the test by 11:59 tonight. So you have about 12 hours to do it. So, and then, like I said, it'll probably take you just about 30, maybe 45 minutes. I don't anticipate that it'll take you the entire time, an entire class period to do it. But the reason why I want it done by tonight is simply so that I can grade it this weekend. I'll be able to get your scores back to you and you should be able to see which ones you missed and what the correct answers were. And then when we meet back up again on Wednesday, I'll go over it. I'll go over the test with you and see if you have any questions. And then our next unit of study, believe it or not, is one of my favorites. It's kinetics. Kinetics is a lot of fun. It's all about reaction rates, and that's what we'll be getting into next. Okay, so that's what you can look forward to when we meet again on Wednesday next week. Okay, so if there are no questions, I'm going to go ahead and stop recording. Thanks for coming, guys, and I hope you have a wonderful weekend.